Class. Could I have your attention, please? We've got not very much to do. We've just got a ton of time. Wait. No, switch. We've got a lot to do and not very much time. There we have it. Right. I know. I mean, I've been where you guys are. I know what you guys want, and that is that on a Friday or right before a weekend. I was going to say, but that doesn't need to be said. But anyway, you guys want to actually, I believe, learn about kinetic theory, pressure, and then review the ideal gas law, don't you?
How'd you know?
How'd you know? It's a gift I have, really. Okay. So this is concept 0. Can you scoot back just a tiny bit? I don't know why you're so far forward. Okay. Here is concept 0. Okay. And this is sort of a, we got here as scientists in a rather circuitous way, right? But anybody can feel, this is one of the things we can feel temperature, yes? This is hot, that is cold, okay? But they didn't know what heat was. In fact, the original theory that actually lasted for quite a while was that the heat is actually like this, this invisible fluid called caloric, which can flow through objects, even like metal and stuff like that, right? But we now know, and I'm not going to really expand on that idea, we now know that that it's, well, here's a gas, right? We now know that it's just the motion of the molecules, yeah? There we go. And this gas might be hot, and this gas might be cold. Hot, cold, hot, cold, yeah? There we go. So that's kinetic theory, right? Early clues, by the way, that this was the case is that if you take pine pollen and put it in water and look at it under a microscope, you can actually see the little grains of pollen moving around because the molecules of water are slamming into it, right? And Einstein actually used this to prove the existence of atoms in a paper in, I believe, 1905, right? So in 1905, not everybody agreed that matter was made of atoms, and we've come kind of a long way since then, right? Now, let's further develop this idea because we talk about temperature, okay? And when I say temperature, I mean temperature as in like kelvins, right? Absolute temperature is proportional to the average kinetic energy of these molecules, right? And so look at that as these things bounce around, right? Let's get it going. There we go. There you go. Okay. As these things bounce around, the first thing we got to convince ourselves is that they're all at about the same temperature. I'm watching it because every now and then one of the little tiny guys escapes, and I've got to go find it. Okay. Now notice, if you look at these things, if they all have about the same average kinetic energy, is that possible? Because what can you say about the big ones? Are the big ones going very fast? No, but could they have on the average the same kinetic energy as the small ones? Yeah, because they got more mass. They can go slower and have the same average kinetic energy. That's possible, right? Yeah? Okay, I'm going to turn this down because it's very hard to talk while it's going. Okay. Now, think about this. The small molecules like hydrogen and helium, aren't they going to be going really, really fast? In fact, some of them are going very fast. In fact, they're going so fast that at the edge of the atmosphere, they escape into space. Right? This is why you don't find very much hydrogen and helium in the Earth's atmosphere. That which is there has been recently created and is about to be lost to space. Helium comes from, I think, radioactive decay. Hydrogen, I don't know where hydrogen in the atmosphere comes from. There might be none, right? Okay, so the word helium means sun element. We didn't actually discover it on Earth. We discovered it in the spectral lines of the sun. We looked at the spectral lines and said, that element must be the sun element. And somehow they knew that it was there on the table or something, right? So there we have it. We've got the notion that temperature is just kinetic energy. Faster is hotter. And what else do we need to do? That might be it. Oh, I showed you that. This is good. Okay. Now we need to talk about scales of temperature. So I'll put this out of the way. I know, I like that little thing. Is that what? I got it, some scientific catalog. Okay, here are our temperature scales. Let's pretend like I've got a lot to do and that if I have to constantly be trying to get your attention, that I'll get sort of angry. Yeah. Okay. here's our temperature scales. Okay, Celsius is all about water, so 100 is boiling point, 0 is the freezing point. Okay, if we go to Fahrenheit, and I don't know why this is, but 212 is the boiling point, 32 is the freezing point, and 0 is just cold. Okay, and in fact, that's what it is. Okay, that's what the scale is that basically 0 is cold and 100 is hot in our experience. Can I interrupt, guys? Can we stop talking? Thanks. Okay, so Fahrenheit's just this arbitrary scale. 100 is like the highest temperature he thought we'd naturally would encounter, and 0 was like the coldest temperature, right? And it really doesn't mean anything else than that. No, but 100 degrees we do, yeah. And then water, if you extrapolate, is 212, right? Okay, and then kelvins is the real thing, right? So 0 kelvins is like when I turned the power off on that thing, right? All the molecules were sort of sitting there, right? And they're really not stationary. They couldn't be stationary because of Heisenberg uncertainty. There'd have to be some motion there, right? But 0 kelvins is the coldest temperature you can get to, or that could exist, but we can't actually get to that, right? And so I think what we need to do is make some formulas here. This is the most important one, right? Is that kelvins is degrees Celsius plus 273.15. Celsius is cute, but the real unit of temperature that we need to use is kelvins. Yes?
So, I get that we can't get to 0 kelvins. If we did get to 0 kelvins, would that mean the molecules weren't moving?
That would mean they're moving as slowly as they can. The question is, if we got there, would that mean they're not moving? And the answer is they're moving as slowly as they can move. Yeah. Not 0, but they can't go any slower. Yeah? Okay, they're in their lowest quantum state that they can be in, right? This is the most important thing, is that if I give you Celsius, and I'll give my commitment to you is to give you Celsius when you should use kelvins and make you convert it, okay? That's the least I can do for you, right? I think we can convert, let's make degrees Celsius. I think if you take degrees Fahrenheit and subtract 32, they're kind of on an even footing, right? And then I think you need to have, I think there's fewer of these guys, so I think you multiply by 5/9. Is that the right formula? I don't know. Let's test it out, right? 32 works, right? We get 0, don't we? And 212, if we put 212, subtract 32, we get 180 times 5/9. Is that 100? Is it? I think it is, yes. All right. Okay, and then if you want to get degrees Fahrenheit, I think you need to make degrees Celsius more of them, right? And then add 32. Does that do it? I think so. Kind of, yeah. It's like a thing, right? Okay. Let's hit the right arrow and see if there's anything I forgot. Formulas. No, hey, we're good. Here's a little poem. I had a kid from France tell me this poem. I don't know where he learned it. Maybe in English class, right? Okay, the poem is 30 is nice, 30 is hot, 20 is nice, 10 is cold, and 0 is ice. 30 is hot, right? 30 is not all that hot, by the way. Maybe it's hot in France, but 37 is actually body temperature, 98.6 Fahrenheit, right? So we'd have to say 37 is hot, or I don't know. Okay. I know. Here's a graphic that I got that just puts all the scales the same, right? So right now it's about 293 kelvins in here. Seems hot, but not really, you know. Well, let's try it. Now, if you are talented and gifted, please convert this not only to kelvins, but also convert it to Fahrenheit, just for fun. Not only convert it to kelvins, which is what a really important thing to do, right? Okay, but convert it to Fahrenheit.
Did you find a yellow binder in here?
I didn't. If I did, I would have put it up here.
Thanks.
All right. Have fun, man. Which one are you going to? World or land?